In this lecture, we will continue our discussion on example of metric space. Let us define D on set of complex number C as D Z1 Z2 is equal to modulus of Z1 minus Z2. Then D is a metric. D is a metric on set of complex number C. Given a function D defined on the set of complex number C as D of Z1 Z2 is equal to modulus of Z1 Z minus Z2, we have to show D is a metric on C. That is, we have to show that this satisfies the three conditions for a function to be metric space: non-negativity, symmetry, and triangular inequality. Then D is our metric on C. Now solve this one. Solution. Clearly D of Z1 comma Z2 is greater than equal to 0. Z1 Z2 is equal to modulus of Z1 minus Z2. This is greater than equal to 0, and D of Z1 comma Z2 is equal to 0 if and only if modulus of Z1 minus Z2 is equal to 0. Modulus of this number, this difference is 0 when this number is 0. This difference is 0. That is Z1 minus Z2 is 0. That is, this implies when Z1 is equal to Z2. Okay. Therefore, first condition for is satisfied, that is D is non-negative. And next we are going to check out the symmetry. So secondly, D of Z1 comma Z2 is equal to Z1 minus Z2. If I take minus common here, this can be written as Z2 minus Z1 by modulus. This is equal to Z2 minus Z1. And when D of Z1 Z2 is equal to modulus of Z1 minus Z2, if it is modulus of Z2 minus Z1, that means it is D of Z2 D of Z2 Z1. That is, it is symmetry. This implies D of Z1 comma Z2 is equal to D of Z2 comma D of Z1. Okay. Now we are going to prove the third condition, that is triangular inequality. To prove triangular inequality of this metric, we have to show that modulus of sum of two numbers is less than equal to their individual modulus. That is this one. Thirdly, to show triangular inequality, we shall first show that modulus of sum of two complex number is less than equal to their individual sums. For that we will consider the modulus of Z1 plus Z2 whole square. We are going to check the value of what will be the value of Z1 plus Z2 modulus square. Z2 modulus square, that can be written by definition of modulus that you have studied in your ACS first year. Modulus of Z square equal to modulus of Z. Modulus of Z square is equal to Z conjugate of z, that is z1 plus z2, z1 plus z2 conjugate. Again, by using the property of conjugate, I will get this is equal to z1 conjugate plus z2 conjugate. This is from the properties of conjugate, and this complex number you have studied in your SS posture. So if you simplify this one, you will get z1 conjugate plus z2 z1 conjugate plus z1 z2 conjugate plus z2 conjugate. If I expand this one, I will get this one. But again, using the definition of modulus, this is modulus of z1 square. This is, I will write first this one first, z1 z2 conjugate, and this, in place of this is equal to z1 conjugate z2. This can be written as z1 z2 conjugate of conjugate. If I take this conjugate, this is z1 conjugate, this is z2 conjugate of conjugate, will give the number of it, that is z1 by z2. Okay, so this is equal to my this one is z1 conjugate z2. This is now equal to this one. I can write this in place of z1 conjugate z2. I am writing this one z1 z2 conjugate of conjugate. This is modulus of z2 square. Okay. Now look here. If it is a complex number, this is one complex number. Z1 is a complex number. Z2 is a complex number. Their product is another complex number. So this, if I consider this z1 z2 conjugate plus z1 z2 conjugate, that is this is another complex number z3 plus its conjugate, that will be the real part of that number z3. Here z3 is my real z1 z2 conjugate. So with this is twice the real part of this one. This twice the real part of this one, z1 square plus 2 real part of z1 z2 conjugate plus z2 modulus square. Next, a real part of any complex number set is always less than equal to the complex number. Okay, modulus of complex number. Okay, so this can be written as less than equal to z1 square plus 2 modulus of z1 z2 conjugate plus modulus of z2 square. Now again, use the property this one, modulus of z1 z2. All this property you have studied in your SS first year. So I'm not going into the detail of these properties. So right, in place of z1 z2 conjugate, I will get this one, and this is equal to z1 modulus, and modulus of z2 conjugate and modulus of z2 is same. So in place of this z1 z2 conjugate, I can write modulus of z1 modulus of z2 here. So this is z1 square plus 2 modulus of z1 z2 plus modulus z2 square. So here I will get my required result, that is using a plus b whole square formula. Now if I write here, this is z1 plus z2 whole square is less than equal to modulus of z1 plus z2 modulus whole square. This will give you modulus of z1 plus z2 is less than equal to modulus of z1 plus modulus of Z2. Hence, we prove this one modulus of Z1 plus Z2 is less than equal to modulus of Z1 plus modulus of Z2. Now we are going to prove the triangular inequality for the given matrix. That is, therefore, d of Z1 comma Z2 is equal to modulus of Z1 minus Z2. I am adding and subtracting the same quantity. I am adding and subtracting the same quantity, that is Z3. It will not affect this equality. So Z3 cancel out. Now I will rearrange the term in the next step, then use the property of modulus, that is this property. We have just proved this property. We are going to use this property. So from this property, this is one complex number Z4 and this is another complex number Z5, that is plus this. So using this property, I will get this one Z1 minus Z3 plus Z3 minus Z2. So this, by definition of matrix here, P of Z1 comma Z2 is defined as modulus of Z1 minus Z2. This is equal to my D of Z1 comma Z3 plus D of Z3 comma Z2. Hence, our triangular, therefore, our triangular inequality for D is satisfied. That is this one. This is Z2 and therefore, hence D is a matrix. Hence D is a matrix on C, the set of complex number. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.